We all know there are many rare and valuable gemstones around the world, like rubies and diamonds. But what if I told you that an ugly, imperfect rock could be worth just as much as a diamond? Would you believe it? Take a look at this stone when it's cut in half. Notice the intricate patterns hidden inside it. That's the secret beauty locked within meteorites. That's right, some of them even look like gold. But why are these stones so valuable? The answer lies in what they carry: priceless information about outer space. To give you an idea, if you tried to collect the same meteor that landed in someone's backyard by launching a rocket into space, that mission would cost billions of dollars. But because these rocks literally fall from the sky, ordinary people, with a bit of luck, can find one and make a small fortune. And you could be one of them if you know how to look. So in today's video, we're going to explore what meteorites are, how they form, their key characteristics, and most importantly, how you can identify one if you ever find it. We'll also look at some of the most famous meteorite falls in the United States and discover why these rocks can be worth millions. So what exactly are meteorites? In simple terms, meteorites are fragments of solid bodies from space, pieces of asteroids, planets, or moons, that survived the violent entry through Earth's atmosphere. Each meteorite is a physical sample of the distant past of our solar system, a natural time capsule holding information about the earliest stages of planetary formation. These fragments originate from extremely energetic cosmic processes. When two asteroids collide, for example, part of their material is ejected into space at tremendous speed. Over time, the gravity of nearby planets, such as Mars or even Earth, can capture these fragments and pull them toward the surface. In other cases, meteorites are produced by giant impacts on planetary bodies, like the Moon or Mars, which blast rock material into space. Those pieces can travel for millions of years before finally crossing Earth's orbit. Most meteorites discovered so far come from the asteroid belt, a vast region located between Mars and Jupiter, filled with billions of rocky and metallic bodies of various sizes. Collisions there are common, constantly generating debris that occasionally escapes the main belt and drifts into unstable orbits. Some of these fragments are deflected toward the Sun and eventually cross paths with Earth. But not all meteorites come from the asteroid belt. Isotopic studies conducted at institutions such as NASA's Johnson Space Center and the University of Arizona's Mineralogical Institute have shown that a small percentage of meteorites are actually of Martian or lunar origin. This was confirmed by analyzing gases trapped inside the samples, gases identical to those in the atmospheres of Mars and the Moon. These meteorites are extremely rare and highly valuable, both scientifically and commercially, as they represent authentic material from other worlds. From a chemical and mineralogical standpoint, meteorites fall into three major categories: stony, iron, and stony iron types. The stony meteorites, known as chondrites and achondrites, are the most common. Chondrites contain tiny mineral spheres called chondrules, which formed at the very beginning of the solar system about 4.56 billion years ago, even before Earth existed. These chondrules record the thermal and chemical history of the primordial solar nebula that gave birth to the planets. Achondrites, on the other hand, are more evolved rocks that form through partial melting inside planetary bodies, which is why they closely resemble basaltic rocks found on Earth. The iron meteorites are composed mainly of iron and nickel. They formed in the cores of small planetary bodies, known as planetesimals, that experienced internal differentiation, meaning the separation of heavy metallic material from lighter silicates. When those bodies were destroyed by collisions, their metallic cores fragmented and eventually became meteorites. These often display a metallic sheen and complex crystalline structures known as Widmanstätten patterns, visible when the metal is polished and treated with acid. This pattern is unique to meteorites and cannot be replicated artificially, making it one of the most reliable visual signs of an authentic specimen. Finally, there are the stony iron meteorites, called pallasites. They consist of a metallic matrix embedded with transparent crystals of olivine or peridot. Pallasites are considered the most beautiful of all meteorites, and some slices, when polished, are even used in jewelry. Scientifically, however, they are far more important because they are believed to have formed at the boundary between the metallic core and the rocky mantle of ancient planetary bodies, regions that are completely inaccessible on any planet today. Beyond their composition, the age of meteorites is astonishing. Through radiometric dating methods, such as uranium lead and samarium neodymium isotopic analysis, scientists have determined that most meteorites are between 4.4 and 4.6 billion years old, making them the oldest solid materials known. Some preserve minerals such as forsterite, enstatite, and troilite, which condensed directly from the original solar nebula, the same gas cloud that formed the sun itself. Another crucial aspect is the role meteorites play in understanding the origins of life. In some carbonaceous chondrites, scientists have identified complex organic molecules, including amino acids and carbon-based compounds that do not naturally form on Earth. These discoveries support the hypothesis that some of the basic building blocks of life may have been delivered by meteorites billions of years ago through a process known as panspermia. So how can you tell if a rock you find is actually a meteorite, a true fragment from space, and not just an ordinary stone from Earth? The process starts with close observation, looking carefully at the rock's appearance, texture, and weight. From there, you can perform a few simple tests at home before turning to professional analysis. Most people imagine a meteorite as a dark, irregular rock, and that's a good starting point. However, there are key differences between a real meteorite and common terrestrial materials like volcanic rocks, slag, or iron ore. Meteorites are divided into three main groups: stony, chondrites, and achondrites, iron, and stony iron, also called pallasites. Each group has distinct physical traits that help in identification. Iron meteorites are the easiest to recognize with the naked eye. They contain very high amounts of iron and nickel, typically 85 to 95% iron, with smaller amounts of nickel, cobalt, phosphorus, and sulfur. This composition makes them extremely dense. While most Earth rocks have a density of 2.5 to 3 grams per cubic centimeter, an iron meteorite can exceed 7.5 grams per cubic centimeter, heavier than solid steel. When cut open, the inside reveals a silvery metallic luster and a distinctive crystalline pattern known as the Widmanstätten structure, formed by the slow cooling of metal inside planetary cores billions of years ago. This pattern is unique to meteorites. It cannot be reproduced artificially. In stony meteorites, the appearance is different. Their surfaces are usually dark and coated by a thin, glossy black layer called the fusion crust, created as the rock burns through Earth's atmosphere. Although it's only a fraction of a millimeter thick, it's one of the most reliable indicators of a genuine meteorite. This crust may show a subtle sheen, small pits, or a melted glassy texture caused by intense heating. Another signature feature is the presence of regmaglyphs, shallow thumbprint-like depressions formed by ablation and turbulence as the meteorite passed through the atmosphere. These aerodynamic marks prove the rock endured extreme heat, something that never occurs in ordinary earthstones. Specimens that retain well-defined regmaglyphs are especially prized by collectors and researchers. Inside, stony meteorites are typically grayish or greenish, often containing tiny, shiny specks of metal visible under magnification. These metallic grains are made of iron-nickel alloys that resist oxidation. Some types, like chondrites, display small, rounded structures called chondrules, which never appear in terrestrial rocks. Their granular texture and mixture of silicate minerals with metallic inclusions are strong clues of extraterrestrial origin. When it comes to shape, meteorites are rarely symmetrical. Most are irregular, with rounded edges and rough surfaces, a result of partial melting and fragmentation during atmospheric entry. Perfectly spherical or flat meteorites are exceptionally rare. They also lack visible crystals or the glassy brilliance often seen in Earth-formed minerals. A simple magnet test is often the first step. Because of their high iron content, most meteorites react strongly to a neodymium magnet. If the pull is strong, that's a good sign, but not proof. Certain Earth rocks, like magnetite, hematite, or industrial slag, can also be magnetic. The difference is that meteorites are unusually heavy for their size, and do not leave a black streak when scraped across unglazed ceramic, while magnetite and hematite do. Another easy check is the fracture test. If you carefully break a small, non-valuable piece, the interior of a meteorite usually shows a uniform structure without visible crystals, sometimes with a metallic shimmer. In contrast, most terrestrial rocks break along granular or glassy surfaces, revealing separate mineral grains. Weight is also a quick indicator. A small 2-inch metallic meteorite can weigh more than a rock the size of an apple. This difference in density is immediately noticeable the moment you hold it. For those who want to search more effectively, portable metal detectors calibrated for iron and nickel can help locate meteorites buried just beneath the surface. Professional hunters also use thermal imaging drones to spot density anomalies in deserts or dry plains, where the dark color of meteorites contrasts sharply against pale soil. A common trap for beginners involves what collectors call meteor wrongs. These are earth rocks that look like meteorites but aren't, such as industrial slag, basalt fragments, iron concretions, or rusted metal debris. Real meteorites have a thin, even rust layer with a reddish-brown tint, not thick, crumbly oxidation. Their interiors remain metallic and shiny even after centuries of exposure. To confirm authenticity, the next step is to measure exact density. Weigh the sample, then divide by the amount of water it displaces in a graduated container. A result above 4 grams per cubic centimeter is a strong sign of extraterrestrial origin. Additional properties, such as electrical conductivity and nickel content over 5%, are verified through laboratory testing. These observations and simple tests are essential for avoiding mistakes before sending the specimen for professional examination. They are the first real steps in turning curiosity into discovery, and perhaps finding a rock that truly came from beyond our planet. After performing all the basic tests at home, the most important step to confirm whether a possible meteorite is genuine is professional scientific identification. This is where specialized institutions come in. Laboratories equipped with advanced analytical instruments capable of determining with complete accuracy certainty whether a specimen is truly extraterrestrial. In the United States, the main reference center is the Smithsonian National Museum of Natural History in Washington, D.C. The museum's Department of Meteorites houses one of the largest collections in the world, with more than 45,000 registered and cataloged samples. There, teams of geologists, astronomers, and chemists specializing in meteorites have developed precise protocols for analysis, preservation, and classification. On the Smithsonian's official website, you can find detailed guides with side-by-side images comparing Earth rocks and genuine meteorites, as well as a flowchart that explains the step-by-step screening process. Researchers outline which characteristics should be checked before sending a sample and which types of rocks are not accepted. This initial screening is crucial because it prevents the submission of clearly terrestrial materials, which represent about 90% of the samples received each year. The Smithsonian also offers a mail-in laboratory analysis service, accessible to anyone in the world. The procedure includes instructions on how to collect, package, and label a sample correctly. The stone should be cleaned without chemicals, wrapped in aluminum foil or plastic film, and shipped with details about the location and date of discovery. This information helps scientists correlate the sample with recent recorded meteor events. After the sample arrives, the team performs an initial visual and magnetic inspection. If the material shows promising characteristics, it proceeds to advanced testing. Among the methods used are scanning electron microscopy, SEM, which reveals the internal microstructure and metallic alloys, X-ray fluorescence spectroscopy, XRF, used to determine elemental composition, and isotopic analysis, which measures ratios of radioactive elements, such as uranium, lead, and neon. This last method is essential for establishing both the meteorite's age and its likely origin, whether from Mars, the Moon, or the asteroid belt. Another technique, X-ray diffraction, identifies the specific minerals present in the sample. This type of analysis can confirm, for instance, whether the rock contains olivine, enstatite, kamacite, or troilite, minerals typical of meteorites but rare in terrestrial rocks. Combining these results produces a unique mineralogical profile, almost like a fingerprint, that allows scientists to classify the meteorite within one of the more than 60 officially recognized subgroups. Beyond the Smithsonian, other U.S. laboratories are also internationally recognized. The UCLA Meteorite Gallery in California maintains a dedicated team for analysis and authentication and provides a high-resolution image database for comparison with known samples. The Field Museum of Natural History in Chicago also offers scientific consultation and houses mass spectrometry instruments capable of detecting trace volatile elements. Meanwhile, the Lunar and Planetary Institute in Houston collaborates with NASA on meteorite classification and storage programs, particularly those recovered from Antarctica, which are among the best preserved on Earth due to the cold, stable environment. In some U.S. states, local universities also accept public submissions, either free of charge or for a small fee. For example, the University of Arizona conducts preliminary analyses and maintains a public database that records all confirmed meteorite finds in the country. This transparency is valuable because each verified meteorite contributes to the global distribution map and helps researchers trace potential atmospheric entry paths. Another excellent resource is the Meteoritical Bulletin database, an online catalog maintained by the Meteoritical Society that compiles information on every officially recognized meteorite since the 19th century. There you can check whether a new discovery matches a previously recorded fall or represents a completely new composition, something that greatly increases both scientific and commercial value. Experts also provide detailed guidance on how to properly preserve a meteorite after discovery. The key is to store it in a dry, sealed environment, avoiding prolonged contact with humid air since iron and nickel oxidize rapidly. The best practice is to keep the specimen in an airtight plastic container with silica gel packets to control humidity. Never apply oil, varnish, or cleaning products, as these can chemically alter the fusion crust and compromise future analyses. Anyone seeking a formal authenticity certificate can request one from recognized institutions. This document includes the meteorite's chemical composition, official classification, and registry number, confirming its legitimacy for private ownership, sale, or museum donation. As of 2025, the average cost of this service in the United States ranges from $100 to $400, depending on the complexity of the analysis. Now that you know how meteorites form and how to identify them, let's look at some real cases of meteorite falls recorded in the United States, where science and luck met in truly remarkable ways. The U.S. is one of the countries with the largest number of cataloged meteorites in the world, more than 1,800 confirmed discoveries so far, according to the Meteoritical Bulletin database. That number is due not only to the country's vast and geologically diverse territory, but also to its strong culture of research and astronomical observation. Over the past 2 decades, several events have drawn attention from scientists and the media. One of the most fascinating cases is the Sierra del Carmen meteorite, which fell in 2007 along the Texas-Mexico border. The event was captured by dozens of security cameras, and witnesses reported a bright blue flash in the night sky followed by a sonic boom.
That's a meteor! This is so unreal!
Fragments were recovered within hours by researchers from the University of Texas, who confirmed it was an H5 ordinary chondrite, a common type of stony meteorite, but with an exceptionally well-preserved fusion crust. The main specimen, weighing about 14 kilograms, 30 pounds, is now part of the collection at the Texas Memorial Museum in Austin. Another important case is the Norton County meteorite, recovered in Kansas in 2006. The name actually refers to an earlier fall that occurred in 1948, but new fragments were uncovered during agricultural excavations in the same region nearly 60 years later. The material was identified as an obrite, an extremely rare meteorite made almost entirely of enstatite, a pale magnesium silicate. Obrites are thought to originate from asteroidal bodies that form closer to the Sun, and their composition offers valuable clues about the early heating processes in the inner solar system. Only a handful of museums in the world possess samples of this type. In 2003, another notable event took place in Illinois, the Murrayville meteorite. Local residents observed a shower of fragments after a bright fireball crossed the twilight sky. Roughly 30 pieces, totaling just over 10 kilograms, 22 pounds, were recovered from nearby farms. What made this case special was the detailed documentation carried out by amateur astronomers and meteorologists, who calculated the object's atmospheric trajectory with remarkable precision. Their data showed that the meteorite entered the atmosphere at a speed of 16 kilometers per second, about 36,000 miles per hour, an important value for orbital dynamics research. Another interesting case occurred in 2002 near Ainsworth, Nebraska. Although there were no visible flashes reported, a farmer discovered dark, magnetic stones scattered across his property weeks after a thunderstorm. Later analysis confirmed that this was a strewn field, meaning the meteorite broke into dozens of pieces during atmospheric entry. This case became particularly valuable for studying fragment dispersion, helping scientists better understand how meteorites shatter in flight. Today, part of the Ainsworth collection is displayed at the University of Nebraska State Museum. The Murray meteorite, which fell in 2000 in Kentucky, also holds an important place in history. It's classified as a CM2 carbonaceous chondrite, the same type that contains amino acids and complex organic compounds. These meteorites are intensely studied because they preserve chemical material similar to what existed before Earth formed. Samples from the Murray meteorite revealed stable organic molecules, reinforcing the theory that meteorites may have delivered some of the basic building blocks of life to our planet. For that reason, it remains one of the most scientifically significant meteorites ever found in the United States. Beyond these classic cases, new events continue to occur with surprising frequency. In 2012, the Sutter's Mill meteorite in California was witnessed by thousands and recorded by dashboard cameras across the state. It exploded over El Dorado County with an energy release equivalent to 4 kilotons of TNT, about 1/4 the yield of a small nuclear bomb. Fortunately, no one was injured and fragments were collected within hours. Sutter's Mill also belongs to the carbonaceous chondrite group, and its study revealed organic compounds never before detected in meteorites. More recently, in April 2023, residents of Maine reported a loud explosion and saw a brilliant fireball streak across the sky. NASA's weather radar tracked its path and helped recovery teams locate fragments within 48 hours. This was the first officially confirmed meteorite in the state's history. The small fragments, only a few centimeters in size, were classified as H chondrites, and some were later auctioned for over $25,000 each due to their rarity and the well-documented fall. Another widely publicized incident happened in 2020 in Missouri, when a 2-kilogram, 4.4-pound meteorite crashed through the roof of a home in the city of Winterset. The impact was minor, but enough to break through the ceiling. Unaware of its value, the homeowner posted photos online, which quickly drew the attention of experts from the Central Missouri Astronomical Association. After analysis confirmed its authenticity, the meteorite was purchased by a local museum. These cases show that meteorite falls can happen anywhere, and that public awareness and quick observation are crucial for recovery before weathering or erosion destroys them. Today, most new discoveries in the United States are made thanks to automated monitoring systems, such as NASA's All-Sky Fireball Network, which uses cameras across multiple states to track meteor trajectories and predict potential impact zones. Why can meteorites be worth millions? Because they are literal witnesses to the early formation of our solar system, preserving information about the origin and evolution of celestial bodies. These relics, unchanged for about 4.5 billion years, are priceless to scientists who study how everything began. Most meteorites weigh only about 10 grams, roughly the size of a bean, and burn partially as they enter Earth's atmosphere, producing what we know as a shooting star. That bright streak across the night sky isn't a star at all, but a small piece of cosmic rock burning up as it falls toward Earth. Larger meteorites that survive their fiery descent and reach the ground are much rarer, and that's what makes them so valuable. Each recovered fragment is a one-of-a-kind piece of the universe's history. Museums, universities, and private collectors around the world compete to acquire these samples, often paying substantial sums to own a genuine piece of space. But what about you? Have you ever wondered if there might be a meteorite in your area? Take a closer look at the stones around you. One of them might be a cosmic fragment that has waited millions of years to be found. Examine it, test it, compare it, and who knows, the next great discovery might come from your own backyard. And if this topic sparked your curiosity and you'd like to dive deeper into the world of gemstones and valuable minerals, the physical book Gemology Journey for Beginners is available now on Amazon in the first link in the description. This book brings together, in a clear and practical way, everything you need to start identifying gemstones and recognizing real mineral value, the same methods we use here on the channel. Now that you know everything about meteorites, click on the video appearing on your screen to discover where real diamonds found in rivers actually come from. Thanks for liking and subscribing. Good luck, Gem Hunter.